So, the natural topic is, we know how to describe a wave, how does it interact with the material medium. Okay. You need a material medium to support the wave. Okay. So, you can generate the wave, then it is air, and then you have to send it into the body, then it becomes tissue. So, you need to know how the wave is going to interact, wave as we described in equation, how does it going to interact when it is sent into the body. So, we will first introduce couple of terminologies, right, and then we will talk about the interactions. Okay. So, we will start with the impedance, and then amplitude, intensity, remember very similar to how we covered X-ray also. First the flux, photon flux, fluence, right, intensity, that is how we defined, and then we use that in our interaction. Similar thing we will do here. First is your acoustic impedance. What do we mean by acoustic impedance? Okay. What is acoustic impedance? Right, it is strictly defined as the ratio of pressure to resultant. So, what is it that we are doing? You have pressure, you are applying pressure difference, and the pressure difference is giving rise to particle velocity. Okay. So, impedance means, remember your analogous to your mechanical, right, analogous to electrical system that you may be familiar. Your pressure is the driver here. So, in electricals it will be voltage that is the driver, the voltage difference drives current. Here the pressure difference drives, that gives rise to velocity. So, what do you have the connection between V and I, that is your driver, and what is flowing? Oh, V and I is your resistance, right. If it is having frequency, it is right, you can talk about impedance. So, here you have pressure and the particle has to vibrate, right, particle has a resultant velocity. So, impedance is very similar. So, your Z is your acoustic impedance, in this case is the ratio of P by V, the driver and the velocity, clear. So, in some sense you could get a feel for why it is defined that way, why the name comes as impedance, but it is acoustic impedance. Okay. So, P by V is your acoustic impedance, and this is a very important quantity. Why? Because it is, you can get a feel for it, right. You can already sense that each material may behave differently, right. So, your Z in some sense is related to the inherent material property, okay. But we already talked about material property, we already used some other terms as well, right. So, most commonly it is defined in terms of material property and is referred to as characteristic impedance. Why is it characteristic impedance? Because if I tell you the impedance value, it will relate to a particular material. That is why it is characteristic impedance, it is a material property. Okay. We talked about something else as well. Oh, C. Okay. We talked about C as another material property, right, and C was related in terms of your density and compressibility. So, you look at the different properties, all related, but these are all characterizing the medium. So, acoustic impedance is a parameter that is capturing the material property as well. So, you can clearly relate your Z to rho naught C. Okay. So, your, why is this characteristic impedance? Because it is of a particular material. So, Z is your rho naught C. Okay. So, if you do that, it has its own units, right. So, kg per meter cube is your density, C is your velocity, so it is meters per second. So, you have kg per meter square second. However, it is mostly called in rail. What is this rail? This is in honor of a pioneer, Lord Rayleigh, right, Rayleigh theory of sound. So, Lord Rayleigh's contribution is immense to this field, and in fact it is a very old subject in that sense. I think he did is one of his classic books came in 1885 or 1895 or something like that. So it's close to more than 140 years or 130 years ago. So it's a very established stuff. So he's done, Lord Rayleigh's contribution is immense, and therefore this units is in honor of that, called Rayleigh. Okay, so this is one way of writing it. Alternatively, because we have the C, we also encountered in our wave equation, and we saw that 1 by C square, you wrote it in terms of compressibility and density, right. So I can substitute for that. So I can write the Z is rho naught, C is 1 by square root of, so there is an alternate form also you can write. Okay. But I think this is a very standard way to remember. Z is equal to rho naught C is a characteristic impedance, is a very handy relationship. Okay, so that is your impedance. So it can be actually, we have assumed a lossless plane wave equation. So right now we have just talked about a plane wave, there is no loss. So Z is a real number. Okay. Because of this assumption, but reality that may not be the case. As we will see, like with other cases, energy is going to be lost in one form or the other. There is going to be some loss, right. We call as attenuation, right. Here also we will have attenuation, and so in reality it is not lossless, but for now the way we have done it is okay. Z is a real number. It can be complex in reality because of the attenuation. Okay, so impedance. Now then the question is, what is a feel for, what is this number? So for water, right, we said human body, we are about water bodies. So what is the impedance value of in water? So if I try to send the pressure wave in water, what will be the impedance encountered, right, at some temperature at 35 degrees, what is your Z? Okay. Take the log book, you will be able to find the density, right. What all do you need? You need speed of sound, you need density, right. These are there in the log book. If you take that, you can get your Z to be 1.5 into 10 power 6 Rayleigh. By itself, really this does not convey much apart from its factual information. Where it becomes interesting is, so if Z for water is this much, right, what are the typical property, what are the typical materials that we are going to encounter in human body? Fat, muscle, right, water you already have, bone, right, all of these different things, air. Okay, what are those values? Oh, it turns out you see that apart from these two, fat, water, muscle, liver, all of them are about similar, right. Second decimal, first decimal changes, 10 power 6. So very small difference between the different materials. What is completely different? Air, orders of magnitude difference. Lung is slightly different, but then notice, where do you get air in the body? Oh, inside the lung, right. So how do you get to the lung from outside? Oh, you have to cross skin, fat, muscle, and then you get to the fat, right, then to the lung. So now the question is, this tells you a important information. We will not cover more than that here, because we need to talk about the interactions in more detail. But you recognize here that because of this impedance difference between the various tissue types, right, ultrasound is inherently useful only for certain clinical applications. In fact, it is useful for vast majority of the clinical applications, but you will notice that some of the applications, for example, lung imaging or seeing inside the lung, it's usually chest X-ray is what is done to detect lung nodules or whatever. Ultrasound is not that popular. Okay, so you are going to see the effect of that. That is because of, you see this huge impedance difference between lung, air and the other material that are there in the body. Okay, so we will just leave it, recognize that here, but we will come to it in the subsequent slides. Okay, so then how do you, again we talked about this number of photons and photon intensity in the previous X-ray based modality. So here again you have amplitude and intensity. What is amplitude? What we have been dealing with, pressure amplitudes. So pressure is the maximum, or right, the value of the pressure. Okay, so here this, what does this do? It quantifies the tallness of the waves that were showed. So in some sense you can relate, if you talk about sound, not just ultrasound, sound, right, because ultrasound is just frequency is different. So if you take amplitude of sound, you will relate it to the loudness, increase the volume, decrease the volume, right, that has to do with your amplitude. Whereas so larger the amplitude, higher the accompanied wave pressure. That's why you increase the too much volume, you know, your eardrum, you may get pain, because it is trying to push the eardrum back and forth, right, your frequency is not changing, it is the amplitude. Okay, so amplitude. What is the intensity then? Oh, intensity has to do with some square term per area, right. So intensity is the amount of acoustic power per unit area. So you had amplitude, intensity is your power per unit area. What is your power? Okay, I have my intensity as power by area. What is my power? Oh, power is you know, I am just trying to, I can just give out your formula, but then I think it's a good exercise to start from the definitions and then build your way, so that there is no confusion in the end. Okay, so amplitude, no issues, that is your P that we have been talking about, the pressure amplitude. When we talk about intensity, we are talking about, intensity is nothing but your power per area. Power is nothing but work per time. How much work can you do per time? Work per time. But what is work? Oh, work is force into displacement or distance, right? Force into distance by area into time. Now if you conveniently look at it, we have certain terms of interest. Force per area and distance by time. What is force per area? That is your pressure. What is your distance by time? That is your velocity. So I can essentially get my intensity is nothing but pressure into velocity. Notice that this velocity is not the speed of sound velocity, not the velocity of the wave. This is of the particle. So this is another, there is a velocity of the particle, there is a velocity of the wave. These two are two different things, don't confuse. Okay, so I is pressure into velocity. This is your intensity. Okay, so from what we have done, right, we already covered impedance. So using that definition, we can write P, we can change the velocity as P by Z. So you get P square by Z. So your intensity is pressure square by Z. Right. So intensity is, you have amplitude, square of your amplitude divided by Z, your impedance. So this is a handy, that impedance itself, right, relating particle velocity and pressure itself will be used very conveniently in the description of how this pressure, particle velocity when the wave is moving, to describe its interaction. Okay, so this is intensity. So now the question is, okay, I have this wave, I know how to describe this wave, I have used certain terms now to describe the different medium. Medium 1, different medium 2, they can be different in terms of Z or C. Z is your acoustic impedance, or your C, speed of sound, density, compressibility, right. So now the question is, what happens if I encounter a different medium? So I send the wave, and now the wave is going to go from one medium to the another medium. Then how do I describe it? What are the interactions and how do I describe? So you have going to talk about reflection and transmission of ultrasound waves when it is going from one medium to the another medium. Okay. So when we talk about reflection and transmission, the two things we have to answer: what is the angle and how much is the amount. So I have a pressure wave or the sound that is going in one medium. I have another medium I am encountering, so I have something that is coming back, something that is going to go further down. How much is going to come is one aspect, how much of it is going to go forward, right, that is one aspect. Where is it going to come, what angle is it going to come, what angle is it going to go further, that is another aspect. So there are two details that we need to know, right. So the angle of the reflected waves, angle of the transmitted waves, or the percentage of the incident power that is reflected back into the same medium, and the percentage of power that is going forward. Okay. So let us take two mediums, medium 1 and medium 2. Again, our interest is not going to be in the derivation. Okay. We are just going to recognize what it is, and maybe you can get a feel for it when we relate it to something that you probably know from your high school with the optics. Okay, medium 1, medium 2. What have I drawn here? These are the plane waves, plane wave fronts, right, just to describe. These are plane wave, the solid line that you are seeing are capturing the plane wave front. So for example, this line captures all of them at high pressure, right. So this is the next high pressure. So that means distance between the two high pressure peak to peak is your lambda. So in between it is all going down and up, but I am just representing, because it is a plane wave, I am just putting this line to describe that plane that is propagating. Okay. All of the phases are also traveling like that only, so no problem with that. So your lambda, so when it is going like this, right, it is going, I have an interface, right, I have an interface, it is hitting the interface, coming back in the same medium, and some of it is going forward. So I have a wave that is coming, I have an interface, on the same side wave is coming back, in the forward direction some amount is propagated. That is what this plane waves, here it is the dotted lines are the reflected waves, the solid line are the transmitted waves in the medium 2. So you have law of specular reflection, which states that theta I is equal to theta r. So I hit at theta I, angle of incidence, angle of reflection, theta I equal to theta r. Of course, you can talk about, from the geometry you can talk about the d is here. From the geometry here you could talk about d is lambda 1 by sin theta I, that is on the incident side, but d is the boundary. So d has to be matched on the other side as well. So d should also be related to lambda 2 and sin theta 2, theta t. Okay. So if you, of course, your lambda 1 and lambda 2 are not same, because these two are two different mediums, correct. Same frequency, this is C1, this is C2, therefore lambdas are to be different, correct, because these are two different mediums. C is equal to f lambda, remember, if f is same, right, C is different, lambda will be different. So that is what, so lambda 1 is not equal to lambda 2. However, at the boundary of this, or the interface of the two mediums, you cannot, it has to be same, it has to match, right, otherwise the interface will give away. So this has to match, and therefore what you can get is this relationship. This I am sure you would have seen. Where would have you seen this? Oh, sin theta I by sin theta t is equal to C1 by C2 is very similar to your Snell's law in optics that you would have studied, same Snell's law. So when you are reviewing the Snell's law, when you are reviewing this, you will also understand there is one another important angle. What is it? Critical angle. Okay, critical angle above which what will happen? There everything will be reflected back, total reflection. Same concept holds good here as well. Okay. So the angles we know, theta I equal to theta r, and we can relate the incident angle to transmission angle in terms of these parameters. Okay, so much for angle. What is next? Okay, how much is coming back, right? Magnitudes of reflected and transmitted waves. How do we get that? Again, we will draw a simplified version. Here I have taken the liberty to just draw one line. This is just perpendicular to the plane wave fronts, right? This is just the line direction that is perpendicular to the plane wave front. So I have just reduced, I have taken all the dashed line and solid lines to make it little clear. But essentially what you have seen here is, I have a theta I, I have a theta r, but now what should be the case? Oh, I look at this, this is the boundary condition. So the whole idea is the medium is going to support the wave propagation. That means at the interface cannot tear apart, right? Some amount should go back, some amount is going forward, but you cannot, the interface cannot tear apart. That means it has to satisfy a boundary condition, in fact two boundary conditions. One is in terms of velocity of the particle, the medium, right, that particle that is there at the interface, that has to be satisfying certain constraints so that it does not tear apart. Likewise the pressure, you have two pressures, right? On one side you have one pressure, the other side you have another pressure. So pressure has to balance. If there is no pressure, does not balance, then also you have a chance of rupture of the interface. So what are the boundary conditions? Your pressure on both sides should match out at the interface. So your PT should be equal to Pi plus PR at the interface, and then the component of velocity, right? That's what is the component? Here is the cos theta t. So Vt cos theta t, that is trying to pull it this side, should also, right, Vt cos theta t, Vi cos theta I minus Vi cos theta I minus Vr cos theta r. So here one velocity is going this direction, velocity is going in the other direction, reflected. So you get the negative because of the directionality, right? So you have Vr, Vi cos theta I minus Vr cos theta r should match out Vt cos theta t, right? So that has to be balanced. Then the pressures on either side also has to be balanced. Okay, so if you do this, then what is the amount that is reflected? Oh, reflected amount is nothing but whatever is reflected by whatever is incident, right? You could talk about reflection coefficient, a reflection amplitude reflection coefficient, because this is just pressure. So these are pressure amplitudes. So amplitude reflection coefficient is the pressure that is reflected to pressure that is incident. Okay, so you can then do subtle rearrangement, use the, right, we know the relationship between pressure, velocity and impedance, right? One side it is Z1, the other side it is Z2, correct? So we could use that relationship and write it in this form. I think there are several ways of writing it. I think the textbook they are writing it as Z2 cos theta I minus Z1 cos theta t divided by Z2 cos theta I plus Z2 cos theta t. Okay, so just different forms of writing, but essentially you get what is reflection coefficient, the ratio of reflected pressure to incident pressure. Likewise, what is your we will just observe this and move. Basically you get the feeling, we talked about some reflectivity, right? You get what it is coming from, where it is coming from, some reflection is there. So we will kind of see how this can be seen as the reflectivity that we are going after. What is going through is your transmission, which is Pt by Pi. You can get this. Okay. Of course, so this is with respect to reflection and transmission coefficients of amplitude. Okay. So what other possibility is there? What we talked about, you have your lambda, right? We talked about a specular. There is another thing where it is called as specular interface reflection, where your lambda is much smaller. This is the interface, right? The interface that we drew. You notice the interface that we drew like a line. There was no roughness. Okay, it was very smooth line that we had. So when the lambda is far less than the dimensions of the smooth interface, we encountered what is specular interface reflection. So we had theta I equal to theta r in R. So what happens if you are 90 degrees perpendicular incidence, right? So perpendicular incidence is a simple case where you have an interface which is a smooth interface, you Pi, Pr. So what we had, the equation is in terms of theta, cos theta t, cos theta I. Here we have 0 degrees. So cos 0 will be 1. So essentially you will talk about amplitude reflection coefficient in case of perpendicular, right, reduces to a simpler form. R is Z2 minus Z1 by Z2 plus Z1. This is your amplitude reflection. You could have your intensity reflection coefficient as square of this. Intensity reflection coefficient is square of this. Likewise, you can do the transmission as well. Okay. So that is not a big deal. Let us take an example just to get a feel for what it is. If you have a fat liver interface, so send the sound waves are going, they are traveling in fat and now they come encounter a liver. So what happens at the fat liver interface? Well, we know the values for fat, we know the values for liver, right? If you look at the table that was shown few slides ago, we had Z for liver, Z for fat, Z for water, right, your acoustic impedance. So now what is the R? R, amplitude reflection coefficient, is going to be Z2 minus Z1 by Z2 plus Z1. Z2 is your liver, Z1 is your fat. So what is going to be the reflection coefficient, right? R is Z2 minus Z1 by is only 0.1. Okay, before we comment about this little bit further, let us see what happens if you have two other materials, for example mussel and air. Same thing, go to the table that we had. If it is mussel air interface, when you have perpendicular incidence, you have Z2 minus Z1. When you substitute, what do you get? You get 0.99. So now the question is, okay, one is 0.1, the other is 0.99. What is good, what is bad, what is desirable, what is not desirable, how do we put to context these numbers that we are seeing, right? So there is a thing, there is a good and a bad. So what does that reflectivity says? I send sound wave in. If the wave interacts, when it goes to the fat liver, right, it goes through the fat, it hits the liver. When it goes, that happens, R is 0.10, that means only 10% of the amplitude, the pressure actually reflects back to the medium. So in this case, for example, I am sitting outside, I am sending the sound waves in, it goes through the fat, it encounters liver, only 10% of it comes back. So if I have to capture this, what is coming back, and then say you came back from this location, or there is an object, there is an interface at that location, then this quantity is going to be very small quantity that I am getting. That is the bad side. The good side is, oh, that means there is 90% of the amplitude, right, that is still there to go further. So I can come with fat liver interface, I will have enough pressure to actually go inside the liver and perhaps come outside the liver, and therefore when I am sitting outside, I can see through the liver. I can see through from fat to liver, and through the liver, and maybe liver to the surrounding muscle at the back side of it. So the good news is little reflection happens, and therefore you have enough strength, enough pressure wave to go further down, go deeper. Okay. The downside is I am getting an echo back, but I am getting reflected signal back, but the quantity is less. Okay. So in relation to this, what do we interpret? Oh, so here what is happening? I have muscle air interface is 99%. Oh, here I get lot of signal back. 99% comes back when it enters, when it encounters this interface. Just to make it vivid, let's say I have air muscle interface, right? So air is outside, muscle. So when I start with the skin and I get muscle. So when I send the sound wave, I have a way to generate my sound wave, ultrasound. I am putting it into the body. Okay, what is going to happen? I am going to encounter air muscle interface, right? What happens when I encounter air muscle interface? 99% will come back. That means I generate this sound wave, ultrasound wave, try to put it into the body, but because air is on one side, that is outside the body, and muscle is inside, right? Two different Z's, I will not be able to send sound inside the body. Then how will I be able to see what is there inside the body? If I cannot send, 99% comes out at the skin, it just bounces back, right? So this is a troublesome thing. So what typically they do is, when you go for if you have been for an ultrasound imaging, what they do is they put some acoustic gel, coupling gel they call. So they put acoustic gel that displaces the air, then we have this wave generator that will be placed in that gel, so that the sound, that is ultrasound, that is generated goes through the gel and goes through the tissue. Therefore, you do not have air in between. If you have air in between, you will have air muscle interface and you will not be able to penetrate inside the body. This is the reason when you go towards the lungs, right? When you go towards the lung, it is there inside. So muscle, when you go towards the lung, one side is, inside is air, outside is some other soft tissue. So you are not able to penetrate the lung. So this is a very practical, I should say, constraint that you will encounter. Last but not the least is your attenuation, right? What is attenuation? Anything when there is a loss. This is how we have been talking about, right? Anything when there is a loss. Here what are the losses possible? Oh, you can send the sound and the sound can go in different directions, right? Or it can get absorbed. You are talking about particles that are vibrating. So maybe it will take some energy and, right, it will not be able to, there will be some loss, absorption. Okay. So a sound beam travels through the tissue, its intensity decreases as a function of distance. Okay. So we do not care about what it is, there is a loss, and this we call as attenuation. Okay. So what are the possibilities? Sources for the loss, a reflection and scattering at the interface. So I am sending the signal, some signal we just calculated, right, R comes back. So that means if you are downstream, right, as you go further in depth, the signal is reducing because some amount is reflected back, because you had some interfaces scattered, right. So you could not just come at one direction, you could go in several directions. We will talk about that in a minute. Absorption, where again, this acoustic energy is getting converted to heat energy. After all, you have particles that are mechanically moving. So there are going to be friction, there are going to be loss due to absorption. Okay. So typically what we call as attenuation coefficient, it quantifies the degree of loss, right, degree of loss in amplitude with distance. Most commonly we call it as dB per centimeter, decibel loss per centimeter. It is represented as decibel loss per centimeter. However, it is also known, right. So the alpha is dB per centimeter using a particular frequency. Okay. So in a material, for example water, it is very less, 0.0002 dB per centimeter, whereas if you go to muscle, it is 1.2 dB per centimeter. So now you see the challenge. Alpha is also using, this is reported per megahertz or using 1 megahertz. Okay. So depending on the distance you are traveling of the tissue type, the signal is going to get lost, reduced. Okay. So now you couple this with the small r that we are going to get from a typical soft tissue, fat, muscle, right, very small r. So you see the quality, the signal level that you are going to pick is going to be very small. Okay. Why we said using 1 megahertz? Because depending on what megahertz you are using, right, we call as frequency dependent attenuation. So if I increase the frequency, right, if I increase the frequency, the attenuation will also, the amount of loss is also going to increase. So it is dependent on frequency that is operated. Why would I want to, so the question would be, why would I want to then use higher frequency? Because the signal is reduced, I want to probe deeper into the body. So why don't I just use a smaller frequency? Why should I use higher frequency? Remember the relationship between F and C and lambda, right? For a given medium, if I increase F, what is going to happen? Lambda is going to reduce, right? So if I decrease frequency, lambda is going to increase. And we talked about lambda being something related to resolution. The smaller it is, the better the resolution is. Okay, sub-millimeter, we calculated one example as well. So the idea is, if I want to increase the resolution, I will increase my frequency. But if I increase my frequency, the depth through which the signal will go, right, is going to be reduced, or attenuation is going to come into picture. So the signal that you can capture and measure is going to become less and less with depth. Okay, so this is an inherent trade-off in ultrasound that you will face. Higher the frequency, lower is what we call as the penetration depth. Okay, better will be your resolution. Okay, so rule of thumb for most soft tissue, you can get about half a dB per centimeter per megahertz. So depending on your problem, acceptable level of image quality, acceptable level of image quality in terms of SNR, in terms of resolution, you pick a frequency of choice. So depending on, that's why you see, we will do that in instrumentation as well, but you will see that when you go for a abdomen scan, they will use a different transducer. When you go for some other, say, thyroid or heart echocardiography, they will use some other transducer. So all this changes, or frequency they use is different, because depth which they want to interrogate is different. Okay. So absorption and scattering together cause the pressure intensity to decrease. Again, we are modeled this as exponential decay, very similar to what was done in our X-ray as well. Okay. So as you propagate with the distance, there is the exponential decay loss. So if you have a forward traveling wave, right, P of z comma t, which is what we want to consider. When you have that, so at z equal to 0, at source, right, at z equal to 0, you start with an amplitude A naught of a pressure function, right, a sinusoid, cosinusoid that we started. So you can have some amplitude of that. But what happens after it travels certain distance, right, if there is no attenuation, is straightforward. Your P z of t will be whatever is the amplitude A z of t, f of same wave equation that we had, right. So it will have, but if you have attenuation, what is going to happen is this, this has to be A naught, this has to be A naught. Okay. So at z you will have the same A naught, whereas when you have attenuation with the distance, you are going to have a loss. So you are going to have Az will be A naught, whatever you started with the distance you have lost in an exponential format. Amplitude attenuation factor in centimeter inverse. Okay. So, your Pz of t is including your attenuation is a naught, whatever you started, you have some loss e power minus mu a z of this waveform that you started with. Of course, there is another units, right, they play with, which are because your mu a can also be written, right, you have exponential, so you can write this in terms of natural logarithm 1 by z ln of a z by a naught. So, here it is called as Nepers per centimeter. So, clearly you can see a relationship between your mu naught, this natural logarithm, but we also talked about attenuation, right. We talked about this is amplitude attenuation factor, but just before we called something attenuation coefficient. Okay. So, there should be a relationship between those two. So, let us see, since 20 log 10 of Az by A naught is the amplitude gain in dB, a straightforward definition, Az by A naught 20 log 10, right, because it is amplitude. If it is 10 log, then it is power loss, it is 20 if it is amplitude. So, 20 log 10 of Az by A naught we know, right, is in dB. Attenuation we know, attenuation coefficient alpha was in dB. So, now I can relate, here I see this is in natural logarithm. So, I can relate these two as alpha is 20 log 10 base E of mu A. So, this is approximately 8.7 mu A. So, your alpha, which is your attenuation coefficient in dB per centimeter, is nothing but 8.7 mu A. What is mu A? Is your amplitude attenuation factor. You can have Nepers per centimeter. So, if you have that, 1 Neper is about 8.687 dB. So, you have to be very careful when you read the question, right. Make sure the units are appropriate, whether it is in dB or Nepers, you have to have this conversion that you have to do. Okay. So, that is with respect to your attenuation. Last but not least, very important is we talked about scattering, right. We talked about reflection, right, theta I equal to theta r and smooth interface. So, now what happens if you have a rough interface? What do we mean by that? Roughness is size comparable or less than lambda wavelength. So, everything is an object, you have an object whose size is much smaller than your lambda. Lambda is also a length scale, right. So, object dimension is less than your lambda. So, what we saw in the smooth interface, the specular case was the object size, right, the interface was much larger than your lambda. Whereas, what happens if your object size is much smaller than your lambda? That is the case what we call as diffuse reflection or scattering. Two things that you see, this is what we saw, theta I, theta r. Whereas, here notice theta I, no theta r, it is going in all, that is why it is called scattered. Notice here it was flat, whereas here you have imperfections, you have roughness. So, the object size here is that roughness is, you can think about the radius of this roughness, right, length scale, that is comparable or less than your wavelength. If that is the case, then you have scattering or diffuse reflection. This is very important. What you vividly see is it has plus and minus. What is the advantage? Advantages is less dependent. So, if I send a signal, if I send a sound wave, I do not need to know the orientation of my interface. See, if it is a smooth interface like this, if I send a wave at certain angle, I need to know what angle I send, so that theta r, I can receive the signal that is coming back by placing a receiver at that angle of reflection. So, I need to know this. How will I know what is there inside? That is the whole idea, I want to see inside. So, that is going to be challenging. Whereas, here what this is saying is, no matter what, it is angle independent. You send it in, if such an object is there which is less than your lambda, then it is going to reflect in all directions. So no matter wherever I place, I will get some signal. So the advantage is it is angle independent, but the disadvantage is it is scattering all around. So wherever I am picking, I am going to pick only a small portion of, so I am going to have very limited signal, right. So it is going to be very low amplitude in multiple directions. Unless I pick all the direction, I am going to essentially have little signal, okay. So this itself is important, scattering is important, because it turns out when we talk about organ, we talk about the outer interface that we talked about when we calculated our R. That is only specular reflection is okay, but predominantly the object itself, right, liver or all the tissue itself, it turns out that you can think about it as having very small acoustic scatterers are spread in the body. So all these tissue are nothing but collection of acoustic scatterers. Okay, there are small imperfections, interfaces. It is not like one homogeneous medium surrounded by one wall. It is not like that, right? Because you have cells, you have collection of cells, right? So the idea is you have small interfaces, meaning small acoustic scatterers, small in relation to the lambda that we are using. About 0.5 or 0.5 mm is the lambda, right, we saw. So you have acoustic scatterers that is distributed in our body, okay. So our interest is, if you have a object which is a point object at some location D, and I send my plane wave which I know how to write, right, what is going to happen here? Oh, it is going to go as a plane wave, but when it is going to hit the point, right, it is going to scatter all around. What does that mean? That means you can now treat this point is going to reflect everything, and the waves or scatter everything, right, and the waves that are going to come back are more close to spherical. So I send a plane wave, this point object has converted that plane wave into a spherical wave. How much of it is coming back? Oh, that depends on the reflection coefficient of that object, right, impedance mismatch between that point object's material characteristic compared to the surrounding, right. So we can actually write our plane wave equation, which we know. We can actually write our wave equation in spherical coordinates, which also we know from before. But how do we relate those two? By relate those two in terms of the reflection coefficient, R, right. So you can write your source wave, which is your plane wave. We know from before, you have A naught e power minus mu A. So this is the one that is coming and hitting, okay. So when an object is much less than your wavelength is located at 0, 0, D, which has with a reflection coefficient, right, it has impedance mismatch, and that impedance mismatch gives rise to a reflection coefficient. So with R, right. So spherical wave is generated. You can write the equation for the spherical wave as PR of T is, this is your R reflection coefficient, exponential of mu AR. So after it comes, it is decaying with R. What is that? This is your source, right. So R FT minus C. So it has gone in one direction, is coming in other direction, right, going towards D. So your R, small r, is nothing but distance from this point 0, 0, D. This acts as your source now. So now this is what you are going to capture. So I am going to send in a wave that is going to be converted by point into a scattered signal. The scattered signal can go in any direction, and if you are going to pick up the reflected signal at any location, this is the signal that you are going to go after, okay. So this is a very important concept. Okay, most of the time you would have seen in ultrasound, unlike your chest X-ray, in ultrasound you have a probe. We'll talk about it when we go to the instrumentation, but in general what you have observed, right, you have a probe which generates the signal and it also acts as a receiver. So you keep it, you are only doing on the same side, you are not doing through transmission. You wouldn't have seen one probe sitting here and the other probe or some instrumentation on the back usually, right. If you have gone for an ultrasound scan, you would have noticed that. So it is on the same side. So the whole idea here is I send a sound signal that gets bounced back because of the material property, how the material is distributed, how the acoustic property, how acoustic scatterers are distributed in the body. Based on that, I get my echoes back. I send the acoustic pulse, I get echoes of that pulse. So typically we operate in what is called as pulse echo ultrasound imaging. So this reflected signal or the scattered signal, right, it can be reflected or scattered, whatever you are going to get the echo. Okay. So this is how you can write that. So we will stop here. This is good with respect to our structural part, reflectivity. We can get the distribution of reflectivity which encapsulates the density, compressibility, which can be talked in terms of either speed of sound or your acoustic impedance Z, right, particle. So all of this is captured in the R. Okay. So now we will have to talk about the Doppler principle, which can be used for our blood velocity, which will be left to the next lecture.